Okay, now we're going to talk about semiconductors. So to remind you here about the band structure of semiconductors, we've got energy increasing here on the y-axis. In a semiconductor, you have a valence band of continuous states, places for energies and places for electrons to exist within the semiconductor. And your bottom band here, it's called the valence band, and it is full of electrons. Because it is full of electrons, electrons are not free to conduct through the material. There's nowhere for them to go if they're trying to shuffle themselves about. You need some empty locations for them to move to. And then you have some gap, the band gap, some amount of energy, before you get to your conducting band, which is empty of electrons, or near empty of electrons. And in order to get electrons to conduct through a semiconductor, you need to somehow provide them with enough energy to make it to the conducting band, or modify this energy landscape in some way to bring the conducting band lower. And just like in a metal, there's a Fermi level here. In a metal, this would be the energy to which electrons are filled to at 0 Kelvin. And you can see that that is not the definition for a semiconductor. For a semiconductor, the electrons obviously aren't filled in the band. They can only go up to wherever the valence band ends here. So what is the meaning of this level in a semiconductor? Well, you can see how it still could be useful, because if you think about what we were doing at the very end of the last lecture, where we were looking at calculating the population of electrons in the conducting band, that depends on where your Fermi level is. Where 0 Kelvin, this is a step function, where nothing will be populated above this Fermi energy. But as you increase the temperature, your distribution can start to creep beyond it. So if your Fermi level in a semiconductor is here right below the conducting band, then you can start to populate your conducting band at lower temperatures, whereas if it's down here, that won't be the case. So you can still determine a Fermi level for a semiconductor based on sort of where your Fermi-Dirac distribution cuts off. The Fermi energy is the energy, it's the kinetic energy of electrons at the Fermi level. And this is called the work function. And we'll talk about that, I think, in the next lecture more, but it is the energy difference between the Fermi level and the vacuum. So at the point at which the electron is pulled off of the semiconductor or metal entirely. So you'll do an example in the workshop where you're calculating how many electrons are in the conducting band, and thus what is the conductivity of, I think, silicon. It's the example that I gave you at different temperatures. But in order to conduct thermally, you need to have enough energy to excite an electron out of the valence band and into the conducting band. And then not only is this electron free to move, but in the conducting band, but now electrons are free to move in the valence band as well. You've created an opening. So this electron can shuffle over there, and then this one can shuffle there, and so on. This would, even though it's electrons that are moving, what you can say here is, like, visually, it's a hole that is moving. So this gap in the electron configuration, if this electron shuffles over and shuffles over, that little gap can move throughout the material. And that hole, that lack of an electron, is just as good of a conductor as an electron because it allows the electrons to move in the same way. You can calculate the probability distribution of where the electrons are, similarly to a metal. First, you have to calculate your density of states, just assuming that this semiconductor is some box that electrons can move through in the conducting band. And your density of states is this sort of square root function. I've drawn it sideways here. So you have a low density of states here, and it increases as you go up in the band. And your Fermi-Dirac distribution, also drawn sideways here, looks like this. This would be a step function at the Fermi level if it was at 0 Kelvin, but if it's not at 0 Kelvin, it has this gradual distribution here. And the electron population is the density of states times the Fermi-Dirac distribution. This is telling you which of those states are populated with electrons. And that gives you something that looks like this. It is just the result of this function multiplied by the very tail of this function. So this is not to scale at all. This population is very, very small because your Fermi-Dirac distribution is decaying towards 0. And so unless you have a significant temperature, the number of electrons that make it up here are very small. But if you integrate this, count all of the electrons up here, you can get the free electron density for a semiconductor. Like I said, holes can also conduct electricity, and so you can kind of invert everything and calculate an opposite density of states for holes and come up with some charge carrier density for the valence band as well if there's a hole that's been created in it. And these populations are equal in an intrinsic semiconductor, as you might imagine. If you move an electron out of the valence band to the conducting band, you must leave a hole behind. So those are equal, and your Fermi level is therefore always right in the middle here. Your Fermi-Dirac distributions for electrons and holes are mirror images of each other around that point. However, if you dope your semiconductor, you can change the relative proportion of holes and electrons and change where that Fermi level is. So a n-doped semiconductor adds more electrons to the semiconductor. And so that is often signified by some additional energy level here. The energy level of your donor, of your doping, your n-doped atoms in your semiconductor, whatever they are. And these electrons raise the Fermi energy and thus make it easier to populate the conducting band. These electrons are a little bit higher in energy. These doped atoms, the electrons in the doped atoms are a bit higher in energy, and they can contribute to the conducting band more easily. And so if you draw your Fermi-Dirac distributions here, density of states is basically the same. You haven't put so many atoms in that you've changed the band gap or the electronic properties energetically in that way, but you've just added this, you've just increased the Fermi energy, essentially. Now you can get a much higher population of electrons in the conducting band and a relatively small population of holes in the valence band. So in an n-doped semiconductor, it will be the electrons in the conducting band that we would call the charge carriers. However, in a p-doped semiconductor, you are adding atoms to your semiconductor lattice that have empty places for electrons to go, and so you're adding sort of a empty states for electrons to go here, just above the valence band, which allows there to be places to put electrons that are thermally accessible, which allows you to create holes. These electrons are not going up to the conducting band, but these electrons can reshuffle themselves in the valence band to have these holes migrate. And so in a p-doped semiconductor, it is the holes that are called the charge carriers. Again, it's still electrons that are actually moving. But if you look at where the gaps in the, where there should be electrons are, holes, those appear to move throughout the structure as electricity conducts through it. And the free electron density in a semiconductor, that's called the carrier density. And that can be either the density of electrons in the conducting band or the density of holes in the valence band. Either can conduct electricity just as well. So if you're calculating the conductivity of a metal, or of a semiconductor, this free electron density N here that you've been using for metals, that becomes the density of your electrons in your conducting band or holes in your valence band, your carrier density. And whichever one of those is higher, that's called the majority carrier. So in an n-doped semiconductor, electrons are the majority carrier, and in p-doped, the holes are. And the dopant concentration is usually larger than thermally excited carriers. So you can approximate the carrier density as just equal to the dopant concentration. So if you have, some number of moles of your dopant, each of which has an extra electron per cubic meter of material, that's just the density of your carriers. Each one of those contributes one free electron or one free hole, or so forth. So you don't have to do often a complicated calculation. You can just use the carrier density of how much you've doped your material for a doped semiconductor. And one thing that is useful to be able to do, however, if you are calculating electron populations, is you need to know how much your Fermi energy actually shifts. Remember, the Fermi level is shifting up or down depending on what if you're n-doping or p-doping your semiconductor. And not only is that important for calculating electron populations, which I just told you often don't need to do because your density is just equal to your dopant density. This is going to tell you the contact potential of N and P semiconductors in a diode configuration, for instance. So there are a lot of electronic devices made of semiconductor diodes, which have one n-doped side and one p-doped side. And at the interface of those two semiconductors, there is an intrinsic voltage that arises that we'll explain here in a moment. But that voltage is going to be equal to the difference in the Fermi level of the n and p-doped semiconductors. Whatever that energy difference is, divided by the elementary charge, will be your contact potential. So it's useful to know how to calculate how the Fermi level changes when you dope the semiconductor. And this equation is just the Fermi energy becomes for electron donors. So this would be an n-doped. Whatever the intrinsic Fermi level was, whatever the Fermi level is right in between right in the middle of your band gap for an undoped semiconductor, it will shift by plus Boltzmann's constant times the temperature times the natural log of the dopant concentration over the free electron density of the intrinsic semiconductor. And similar for the p-doped semiconductor, but this plus changes to a minus. So what happens at this p-n junction when you have a p-doped semiconductor and an n-doped semiconductor in contact? A potential, a voltage is created. Electrical potential is created between the two surfaces. And what's happening is those electrons, those free electrons in the n-doped semiconductor, will migrate to the lower energy holes of the p-doped semiconductor. Remember we just talked about entropy driving why things happen. And your electrons are filling up to a higher energy on this side than this side, so that energy wants to spread out and make the electron levels equal on both sides in terms of energy, just like if you had some bucket of water with a hole in it and some other empty bucket. That analogy we're always using to describe the movement of things. And so those electrons will move over until your Fermi levels align, whatever the Fermi level, wherever the electrons are sort of going to. The level of electrons will level off in both sides of the both semiconductors. And that causes a built-in voltage because you have some positive side and some negative side that has an electric field. And if we look at a picture of this, here is our n-doped side, here is our p-doped side. So imagine, this is silicon. This isn't, silicon would be tetrahedral structure. But each silicon atom has 4 bonds that it makes. And in a n-doped semiconductor, you might replace some of those silicons in the lattice with phosphorus. Phosphorus is similar size to silicon, so it fits in the lattice. But it is in the next column over on the periodic table, so it can form 4 bonds, but then it will still have an electron left over. So this is why it is n-doped. It has these extra electron sites. The p-doped semiconductor, and this is often something like boron, something that's a similar size to your main semiconductor material, atoms, but with 1 less electrons, 1 column earlier on the periodic table. And so, so this is actually not necessarily drawn. I think these electrons should be over here. The boron will form 3 bonds with its 3 valence electrons, and then it will have a gap where it cannot form a bond with the silicon. So the silicon will have an extra electron here that it cannot form a bond with. So this is a hole, because if there was 1 more electron here, then you could kind of fill out these bonds. And this is the junction between those 2 semiconductors, and this is what like a diode looks like. And what happens is, as you might imagine, like we showed on the energy diagram, these extra electrons, turns out it spreads out energy more, increases the entropy if these electrons move over to fill these holes. So you can form those bonds, But what that does is it leaves both sides charged. Okay, so before, if these two semiconductors are not in contact with each other, even though one is n-doped and one is p-doped, it's still a neutral material. One has extra electrons, but these nuclei have extra positive charges to cancel them out. So neither of these semiconductors are charged, even though they're n and p doped. That doesn't stand. That's the sign of the charge carrier, not the sign of the charge of the material itself. But when you put them in contact with each other, you will get charges. The electrons will move to the holes. And so it's actually your n-doped semiconductor, which is this side, that acquires a positive charge at this interface. And the p-doped semiconductor acquires a negative charge at the interface. As a result, the voltage that you get at that interface, here are the equations I showed you earlier for calculating the Fermi energies of the n and p-doped semiconductors based on the dopant concentrations. The voltage bias is just the Fermi level, the difference in the Fermi energies divided by the elementary charge. So you can combine these equations to get this equation if you just want to calculate that voltage directly. But how does this diode work? You know, a diode will only allow electricity to flow in a single direction. It will not flow in reverse. And so this would be the reverse bias direction. And electrons are trying to move this way. And what happens is, if you have the reverse bias, so making the electrons flow this way, the electron on the n-doped side are sort of further pulled away from the interface. And on the p-doped side, the electrons are pushed into the interface. And so your depletion region here, where you have your combined holes and electrons, is increased. You get a larger range of area that has a positive and negative charge. So you're increasing your charges here at the interface. And what happens is this starts to impede the further flow of electrons, because you've built up a much larger negative charge here and a much larger positive charge here. And so electrons that have negative charges that want to flow in this direction will be repelled by this buildup of charge that has occurred. So it takes more and more energy to push them through, and they just won't go. However, a forward bias, you want the diodes will work if you apply the electrical potential in the opposite direction. You're decreasing the depletion layer. You're pushing these, you're pulling electrons out of the bonds here and pushing them onto the atoms here. So you're minimizing your charge separation at the interface, which is fine. Electrons can continue to flow through here. There's no charge building up that's going to repel them. This is a pretty good video from Veritasium on semiconductors, doped semiconductors, and some of their uses that I would recommend watching. You can follow the link here. It's all about transistors and how you use these PNP and NPN junctions to basically make computers and logic circuits. But diodes are not the only utility of PN junctions or semiconductors in general. There are various photoactive semiconductors that instead of relying on some sort of electrical potential to push you over the band gap, use the energy from light to excite electrons from the valence band to the conducting band here. And if these are intrinsic semiconductors, devices detecting light here, and intrinsic semiconductors, that's called a photoconductor. And you can detect light with this as long as your semiconductor has some reasonable absorption cross section. It doesn't reflect light; it absorbs it. But you can also make a photodiode, which is quite common. You've used these in the lab before, which is based on a PN junction. And these photoconductors only work, but basically you apply a voltage across your semiconductor, and normally you don't get any current. But if you absorb light and excite electrons to the conducting band, then you see a little bit of current based on how many electrons you detect. The size of your current is proportional to the number of electrons that have been excited, which is proportional to the number of photons that hit the semiconductor. But a photodiode can work without any power supply, no external bias, no battery. In the same way that photovoltaic devices work, which is you have this depleted region, which has an electric field built into it, right? You've got a positive side and a negative side. And so if an electron is, if light is absorbed in this region and an electron is excited to the conducting band, it will be pushed in one direction by this charge separation. There's an electric field here that will push the electrons one way or another, which generates a current on its own, because you've got that built-in electric field there. And you can also run a photodiode with a power supply. What you do is you put on the reverse bias, right? So you increase the depletion region here on purpose. And then when it absorbs light, there's a much stronger electric field to push the electron out of the depletion region in a particular direction. So if you power a photodiode, you run it in photoconductive mode with a power source, that increases the photosensitive area, because you're only going to be sensitive to electrons that are excited within this depletion range area, which is larger when you apply this reverse bias to it. But it also will decrease the response time. So if you want a really fast time response on your photodiode, you want to run it with a reverse bias, because this electric field becomes larger and it pushes your electron through your circuit faster. And you can run photodiodes in reverse, basically, to become light-emitting diodes. Usually, you use you make your semiconductor more optimized to do this. But you can use any light-emitting diode as a photodiode detector. So if you have a red LED, you can shine red light on it, and you will see a signal. These are basically the same devices. They're just these PN junctions that have some absorption cross-section. And here it is the sort of recombining of these electrons with the holes that end up releasing light. You have electrons going from higher energy to lower energy states. And if your band gap of your semiconductor is in the range of visible wavelength energies, then you'll emit some of that energy as light. You just want to make sure you've optimized your material so that energy is emitted as light, instead of just having an easy way to transfer that electronic energy to the vibrational energy of the atoms in the lattice, which would make it heat up instead. Some other cool uses of P and N doped semiconductors is a thermoelectric generator, where you can have some hot source up here and some colder source down here. And if you have some N-doped semiconductor and some P-doped semiconductor sandwiched in between, you can create the flow of electrons. The charge carriers will migrate away from the heat source. So in the N-doped semiconductor, those free electrons in the conducting band will move away from the heat source. And in the P-doped semiconductor, those holes will move away from the heat source. And if holes are moving one way, then that means electrons are moving the other way. So electrons would flow through this circuit this way in a cyclical manner. Conventional current is defined as the opposite direction of electron flow. So the conventional current would be going this way. And you can, again, use this same device in reverse. If instead of using it to power something, you can use a power source, and you can create a temperature gradient. You can make a hot and cold side of something. This is what most cooling devices are in water coolers. Water coolers are silent, right? If you have a water cooler in the office, it's not as noisy as a refrigerator, which requires the constant compressing of gas. This is quite silent, and it works with this type of device where you have an N- P-doped semiconductor. And so if you pull electrons this way and you pull holes this way, then that is also creating a net direction electrons are flowing around, or the current is flowing around. It should be this way. Electrons would be flowing this way. So you can make things hot and cold with these devices as well. Okay, so that's all I'm going to say about semiconductors, and there are many practical applications. Remember that N-doped semiconductors have extra electrons, which increases the Fermi energy. P-doped semiconductors have more holes, which lowers the Fermi energy. At a p-n junction, you get this depleted region where you build up a voltage bias, a potential at the surface of the interface. And the depletion region will grow under, if you apply a reverse bias to it with a power source, or which will impede the current flow. And that depleted region will shrink under a forward bias of that p-n junction, which will increase the current flow. And make sure you understand how these p-n junctions can be exploited to make transistors, photodiodes, LEDs, and thermoelectric generators / Peltier coolers. As usual, once you understand how something works, then you can exploit that knowledge to bend the world to your will. And certainly, maybe more so than any other field in recent years, the last several decades, knowledge of semiconductors has certainly transformed the way the world works. Any computers and certainly have loads of these p-n junctions within them. So that's it for this lecture.